Hello, everyone. Namaste. Good morning, good afternoon, and good evening. Well, it's late evening here in Nepal. It's GMT plus 5:45, and I hope you are doing all great. This is Suraj Gautam, a civil engineer and a disaster risk reduction and management professional from Institute of Himalayan Risk Reduction, and I'll be your host for today's session. First of all, I would like to welcome you all to our fourth episode of webinar on geoscience for sustainable development. Well, Institute of Himalayan Risk Reduction has been regularly organizing a Himalayan webinar series under the two themes. One is regarding geoscience for sustainable development and the other is disaster risk reduction. So under the webinar series of geoscience for sustainable development, till date, we have successfully organized 3 sessions and today it's the turn for the fourth one. The topic for today's webinar is faulting in the Himalaya. What do the rock tell us? What do the lake sediments tell us? So which will be presented by Professor Dr. Mary Hubbard. On behalf of the organizing team, we are really grateful to our presenter who will be sharing us with her insights and healthy experiences. So we'd like to warmly welcome our presenter, Professor Dr. Mary Hubbard, who is a professor of geology at Department of Earth Science, Montana State University, USA. The session will be moderated by Assistant Professor Dr. Basanta Rajatikari from Institute of Engineering, Tribhuvan University, who is also our visiting scientist. It is indeed an honor to have insights from our distinguished presenter. Also, we'd like to welcome all of our participants who are attending this session. This webinar event is also featured in the Prevention website. Talking about the disaster, talking about the webinar registrations, till date, we have more than 197 registrations from different corners of the globe. To address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction, and we'll be receiving the queries and feedback from our Zoom chat box, as well as from social media live stream. We have been organizing this webinar series on geoscience for sustainable development on a regular basis. We believe this webinar series has been supporting our early career scientists, DRR professionals, academicians, and all the participants. And yes, it is just the beginning and we'll have a long way ahead. So before starting our series for today, let me share some brief introduction regarding Institute of Himalayan Risk Reduction. Institute of Himalayan Risk Reduction is a research institute established with an objective to assess and understand the risks to contribute for the sustainability. Complying with the Sendai Framework for Disaster Risk Reduction, IHRR envisions to understand the risks and application of interdisciplinary knowledge with science, engineering, technology, and innovations to contribute for risk reduction and bridging of academic research with professionals and policymakers for the sustainability. So our team constitutes of professionals with expertise and experiences in the field of disaster risk reduction and understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. So we have been carrying out a number of projects. I would like to share a few of them. Under the collaborative approach, we contributed to the development of a national dashboard for the COVID-19 response. We coordinated with Ministry of Health and Population, and we contributed in the development of a mobile app named Hamro Swasthya, which has been widely used during this information dissemination in the COVID response. Besides, we have also been using the number of frontier technologies, like we have started the urban core area mapping of the capital of Bagmati province, that is Hetauda sub-metropolitan city. And with this, we have also contributed. Our work has been enlisted as a Sendai voluntary commitment. So we have been working on a number of the activities, and likewise, as I have already mentioned, the Himalayan webinar series is also one of them under the two themes. And today we are conducting our fourth episode. And before starting, I would like to share some in-house rules for this webinar. The audio and video of the participants will be switched off. The overall session of the webinar will be recorded. For any queries, the participants can write up in their chat box or in the comment section of Facebook streaming live. Waiting rooms have been enabled, and registered users with their original identity will be allowed to enter the webinar due to some security reasons. Also, I would like to request our participants to rename and keep their name as mentioned in the registered link. And the feedback links will be provided during the session, and we'll be providing the participation certificates from this session. So without any further delay, I would like to move on to our session, and may I request Dr. Basantaraj Adhikari to proceed further with his moderation. Thank you for now.
Thank you, Suraj. Am I audible?
Yes, you are audible.
Thank you, Executive Director, Institute of Himalayan Risk Reduction, for providing me this opportunity to moderate this session to our esteemed colleague, Dr. Mary Hubbard. And we have known each other for more than 4 years or 5 years. When I met her at Kathmandu during the conference, and other when she came for her fieldwork a long time back. And we are always inviting our internationals as well as national geoscientists to present their research and ideas to motivate our colleagues, our undergraduate students, graduate students, to do and to continue research in this field, in geoscience field. Before introducing Professor Hubbard, he's a well-known scientist around the globe, and she is very well recognized in Nepal. And we have requested her to present her research, and she accepted that. And thank you very much, Professor Hubbard, for that. So Dr. Mary Hubbard is a professor of geology at Montana State University in the United States. Her research interests are structural geology and tectonics with an emphasis on mountain building. She began her research in Nepal in 1985 while working towards her PhD at Massachusetts Institute of Technology. Her postdoctoral position at ETA, Switzerland, took her to the Western Alps and the Pakistani Himalaya. Since that time, she has also worked in the Southern Alps of New Zealand, the Mauritanides of Eastern Senegal, the Damara belt of Namibia, the Appalachian and the Rockies Mountains. So almost she worked in every part of the mountainous range. During her career, she has served 17 years in university administration as a department head, a dean of science, and a vice provost of the global engagement. In the last 5 years, she has returned to research in Nepal. In 2017, she was a Fulbright Specialist at the Tri Chandra Multiple Campus, Tribhuvan University at Kathmandu. She has been awarded a Fulbright Scholar Fellowship to return to Nepal in 2021 and 2022. So we are very much happy, to see her again in Nepal, to go to the mountains and most famous region in the world, Mount Everest, and to see the Gokyo Lake and Namche Bazaar again. And, this is the most fantastic place in the globe. And so today she is going to present on faulting in the Himalayas. What do the rocks tell us? What do lake sediment tell us? And so before I invite Mary, I would like to request our participant, please do not do the annotation, otherwise it will be taken as offensive act. So please do not do any annotation, and I request Mary also disable the annotation for participant. Now I formally want to welcome Professor Mary Hubbard to present. So the virtual room is yours, Professor Hubbard. Please go ahead.
Okay, namaste everyone, and thank you very much for inviting me to do this. I'm very impressed with this series and want to thank the organizers, and it's really a great gift to all students in Nepal and all around the world, all who are able to access these presentations. Can you hear me okay?
Yeah, perfectly okay, yeah. We're hearing you.
Okay, all right. Well, I think I'll just go ahead and jump right in here. So give me a second to get this all shared and All right. Can you see the first slide okay?
Yeah, yeah, perfectly. You are audible,
okay.
and we can see your slide. So please close the annotation, okay?
Yeah, I just, well, it said that it was still, so that's good.
Okay, oh, that's fine, yeah.
Yeah, good, okay. Well, again, I'm gonna just jump right in. Thank you very much for the introduction. What I wanna talk about is faulting, and through that, I'll give a little bit of a history of the work that I've done in Nepal too, but also touching on some of the more current topics. But none of this work is my own, so I do want to give a special thanks to a number of people. So Ananta, I've worked with on several different types of projects. My first trip back more recently in 2016 was with Roshan Raj Bhattarai, who's here in the US now. Two scientists from India, Malai Mukul and Vinny Srivastava, have been working on cross faults, and we hope to work together in the future, have just submitted a proposal. And then last year, the National Geographic Society sponsored our work on cross faults. And then I've had students, past and present, who've also been contributors, Neil Seifert, Bibek Giri, and others. I saw David Spencer's name on the attendee list, and I will give a brief mention about some of the work in Pakistan. So I include you as well, David. And then I think it's really important also to mention that the real helpers, or the additional real helpers, are the support the support people who work with us in the mountains. It's not possible to do work in the high mountains without porters, guides, Sherpas that help us. The business in Nepal, Shangri-La Nepal Trek, has handled our logistics, and we couldn't do our work without them. So a shout out to them as well. All right. Okay, so this won't let me advance. I'm just trying to advance the slide here. Do you have control of that?
No, I think if you have any, maybe this size is very big. So you just close again and you start again, I think.
Really? Okay.
Sometimes it happens. I don't know what happened to you.
Yeah, no, I have never had that problem.
Yeah.
All right, so here we go again. You can pull that pointer. Okay, how funny. All right, well, I'll start with this image of the mountain belt. You all should be familiar with it. This is just a Google Earth image. It looks a little grainy on my screen here, but just to give you a picture of the mountain belt as a whole. And the couple of things that I want to point out on this, while we can see the entire range here, are some of the irregularities. And this is going to be important to some things I'll talk about. But if you look at the mountain front, you can see irregularities, some of the dune valleys in various places, the mountain front, small salients and recesses in the mountain front. And then as well, if we look at I'll call it the backside, but the northern side of the range, we also see irregularities where we've got some graben structures that dip down in. And if you look at this region, it's kind of curious where we've got high mountains that protrude more northward than the rest of the high mountain Himalaya. Oh, so is this, again, it's not advancing. We didn't.
I don't know what happened, but it should be moving.
Okay, I'm a Mac user and I'm trying, oops, there we go. So I don't know what's, okay, so we'll take a step back, a little further back to the same image, but now seeing a larger part of the Indian subcontinent. And I think this is a very impressive image where you can really see the sides here and get the sense of India, how it's protruded into the Asian continent. And then in particular, if we look at the complexities and the syntaxes on the east and the west side of the range, important things are going on in those parts of the range. All righty.
Again, are you feeling Are you having any?
Oh, there we go. So I can use these little arrows. So this might work. Okay, so Himalayan faults. I'm just going to go through, let me just pull these up. A few different aspects of faulting. I'm going to just talk about the major faults again as a review. I know you're all familiar with those. Through the talk, we'll talk about some of the controversies. These are controversies that have been here for a long time with the range and some that are a little more recent. And then I want to talk about a newer concept that I think has a lot of importance and something I've been focusing on, I'll call cross faults. And then we'll look at the climate aspect. Okay, this works for advancing. Okay, so again, a bit of review. We know, of course, that India split away from the Gondwana landmass, so split away from Africa, Australia, Antarctica, started its journey northward, and somewhere in the 60 to 50 million year time frame collided with Eurasia. The result was the slicing, I'll say, of the northern margin of the Indian continent into what we see today. So we have a number of faults stacking pieces of that Indian subcontinent on each other. So starting in the north, we have higher grade metamorphic rocks in the greater Himalaya that have been emplaced along the main central thrust over the lesser Himalaya that's been emplaced along the main boundary thrust over the sub-Himalaya and placed, excuse me, over the Ganges Plain along the main frontal thrust. So you're familiar with this story, as well as the normal fault cutting the very top of the range in the South Tibetan Detachment System. And when we look at a map of the Himalaya, a geologic map, we see how laterally continuous these structures are to a large degree. So the color boundaries on this map in the southern part of the image here are the colors would correspond to these lithotectonic units and the fault zones separating those. We're going to take a journey now and take a look. We're going to basically march up through the range, starting on the Ganges Plain, looking more at the landscape than anything, but we do see different types of rocks, and I'll mention that as we go through. So if we start on the Ganges Plain, of course, we know it's very flat. It's got the sediment outwash, it's got the river floodplains of the river systems. Moving northward into the sub-Himalaya, we've got a fair bit of relief, a lot of topography, and we've got basically unmetamorphosed sediments that have been deformed. So these are some of the molassic deposits that were shed off the early rising range that were deformed. Moving higher up section into the lesser Himalaya, slightly more incised topography and a little bit more metamorphism to the rocks in this next zone. The contact between those two zones is the main boundary thrust here that seen in the area around the field camp of the Tri Chandra campus. If we're looking to the west along the main boundary thrust, sub-Himalaya to the left here, lesser Himalaya placed over it. Standing in the same spot, we turn and look eastward, and that fault cuts through the base of this hill. Moving northward into the greater Himalaya. So the greater Himalaya, of course, makes up the high spectacular peaks. These are a higher grade metamorphic rock mixed with Luca granites. The greater Himalaya has gone by several names in the literature, so a few of them here: higher Himalaya, Tibetan slab. And in the higher Himalayan section, we also have the presence of Luca granites. So this image this is an old image, but of the north face of Nuptse. So the Luca granite is emplaced in here in a fairly large intrusion, but of course there are Luca granites scattered throughout in smaller dikes and sills, as well as smaller bodies. And this would be the summit of Everest, the peak of Everest sticking up out the top here. And cutting the top of Everest is the South Tibetan Detachment System. So a lot of it is actually in Tibet and the China side, but it does cut many of the high peaks in Nepal. And this emplaces in a normal sense or extensional sense of movement. It has emplaced the Tibetan sedimentary sequence or Tethyan sediments down against the greater Himalaya. And I won't talk a lot about Tibet in this presentation, but just to take a quick look here, of course, Tibet has got big strike slip faults on many of its margins, but internally there is also a lot of faulting and folding of rocks, including the number of suture zones that we interpret to be the bounds of smaller, either subcontinents, smaller continents, or island arc fragments that were trapped or collided with Asia prior to the India-Asia collision itself. And I like to kind of compare this to the modern day setting. If you picture Australia where it sits today, if it continues its northward journey to an ultimate collision with Southeast Asia, of course, you will end up trapping all of these continental fragments and island arcs in between. This is all what is today largely Indonesia. Will get trapped in between, and we would end up with a series of suture zones like we see in Tibet today. Okay, next what I want to do is journey to the eastern part of Nepal into the Everest area, and we'll look at one of the controversies that's been around for quite a while, and that is inverted metamorphism. So Ganser recognized way back when that along the main central thrust, there was an inverted metamorphism such that you went up through different grades of metamorphism as you went structurally higher in the section, so creating this inversion. And over the years, a number of proposals have been put forward as to why we've got that inverted metamorphism, including just large-scale folding, multiple thrusts and placing different packages of rocks of different metamorphic grade, a thermal response to overthrusting, we'll talk about that in a second, shear heating, meaning frictional heating along the fault, or there was also a suggestion that it was just an apparent inversion due to changes in the chemistry, the original rock chemistry, which has largely been discarded, I think. I'd say that in the 70s and into the 80s, when I started my work, the sort of favored hypothesis had been put forward by Laffour, and this is the thermal response to overthrusting. So if you emplace along a fault a hot block of rock over a colder block of rock, heat conduction over time will relax the isotherms such that the isotherms become inverted. So if you have the thrusting and then metamorphism during this time of thermal inversion, you would get an inverted metamorphic stack. So my work back in the 80s, so this is all kind of old news, and a lot of work has been done since then that's very similar to this, but with some of the more modern calibrations. But we went into this Everest area, and let me just, if we look at the map on the right, you'll see Everest up in the top part here, and this is the main central thrust zone down here in the multiple colors. The reason for the multiple colors is that there are many different lithologies from marbles and calc silicate type rocks to schists to gneisses to some more mafic and so on. So that's the main central thrust zone. It's about 10 kilometers in thickness, or in width. Actually, I'll just say in topographic width here, our map view width, 5 kilometers in thickness or so. But we made a traverse across this area, collecting samples. So this is a cross section, that AA prime shown on the map with the MCT down here. And we collected samples across them to try to quantify this metamorphism, which at the time hadn't yet been done. So it wasn't clear whether this was, that we could see a change in temperatures or pressures, or both temperatures and pressures. And then of course, we had a goal of constraining the timing. So just a look in the field at the MCT zone. So we're standing on a ridge here looking to the west. The Dudkosi Valley is on the other side of this ridge, and the valley down at the bottom would be the Hinku. And I think you can see in here the north dipping section of the MCT zone rocks. So they're dipping off to the right on the slide, north is on the right. And so we were able to sample along that ridge top, as well as some of the trails that go along the the lower parts of the ridge on both sides for this work. Just a look at one of the lithologies. This is the Faklu Augengneiss, and you'll see here asymmetric clasts, which confirm our top to the south sense of shear, our thrusting sense of shear. Just a distribution of the samples across the MCT and up into the higher Himalaya as well, along that same section. And we then used a variety of thermobarometers at the time. So this involves using a microprobe to get the chemical composition of garnets, the micas, both muscovite and biotite, some of the feldspars, and using this top one here is the garnet biotite thermometer. These other three are various geobarometers, so they're more pressure sensitive. And at the time, of course, we used the calibrations that had been done at that time. So again, that's why I say here circa 1988. So the results I'm going to show you are from that time period. Some work's been done to look at these same samples again, or to look at the same data and apply more modern calibrations. There hasn't been a huge change in the results, so I'm going to just show you what we originally found. What we have here are two sort of graphs that are cross-sectional in their presentation. So we're looking at the distance from the kyanite isograd. The kyanite isograd is kind of in the middle of that MCT zone, and then going northward up from there. The temperatures in degrees Kelvin, so you can do the math if you want centigrade, but the important point here is that there's a really pretty well-defined steady increase in metamorphic temperature up through the MCT zone. Beyond that, it's much more scattered, and I think there's a lot going on in the greater Himalaya that maybe affected that. The pressure data is less clear what goes on here. I think initially we interpreted a decreasing trend through there. Later, I've gone back and looked at metamorphic temperatures and modified my interpretation. My original interpretation, if these were decreasing pressures, that would signify that the metamorphism has happened after the deformation, after these rocks were placed into the position they're in today. And so that would fit the model of Patrick Lefort at the time. But later I spent a little more time looking at the metamorphic textures and realizing that the deformation pretty clearly overprints the metamorphism in most places. And my interpretation now is that there's been much more of a distributed shear across this that postdates the metamorphism. We did do some argon 4039 dating initially, and a few years later came back in and did some uranium, thorium, helium. And the samples that we used came from 4 different locations within the MCT zone, to the north in Ghats, and then up in the higher Himalaya up the Gokyo Valley. The important point out of this that I'll just note is this age here in the MCT zone, the oldest age. This is a hornblende argon. Argon age has a closure temperature just above 500 degrees. That's about the same, that's in centigrade. That's about the same temperature that we had for the metamorphic, determined from the metamorphic assemblage and composition. And so we interpreted that age, which was just around 21 million years, as the onset of MCT deformation. So that age has hung around for a few years, though we've got some evidence there's been much younger deformation as well. Our uranium, thorium, helium age, that's these youngest points that are added here to these curves, also suggests some young activity, both in the higher Himalaya as well as within the MCT zone. So just, conclusions from that work was that that the metamorphism predates deformation. That's my current sort of conclusion on that. That MCT deformation could have initiated at about 21 million years, with continuing deformation after that. And that the shearing was synchronous with the granitic intrusion. So about the time we were getting that 21 million year age, the leucogranites were being dated, as was the extensional deformation to the north in a similar time frame. So metamorphism was inverted during distributed shear would be my current interpretation of that. Okay, so kind of since that time, another big controversy, and I'd say it carries on today, is really just how do we resolve the fact we've got extension along the South Tibetan detachment at the same time or synchronous with the main central thrust deformation. Some of the original interpretations were sort of the what I call watermelon seed idea, but where if you're squeezing a zone, it's like putting a watermelon seed between your fingers when you squeeze it, and it extrudes outward. That's similar to what's going on here in the Greater Himalayan series area, that you're squeezing with the convergence of India and Asia, and as this Greater Himalayan series moves outward, you've got extension to the north and thrust deformation to the south. It's really kind of the channel flow idea that was put forward fits that model as well in a way, but with some, for some different reasoning behind it. It would be sort of a squishier, more molten, not exactly molten, but a squishier layer here that's extruding outwards in this convergent setting. So that's channel flow. There have been other hypotheses. Critical taper is maybe a little bit more like the watermelon seed, and then some hybrid models of this. And I'd say the debate sort of rages on, but what we do know is that there is deformation within this section between these two major faults that accommodates some of the exhumation of these higher grade rocks in this area. So it's not as simple, of course, as any of our end member models. Kind of related to looking at the deformation within the Greater Himalayan sequence, when I first went back to Nepal in 2016 after an absence for many years, I went up just north of Namche. This was with Roshan Raj Bhattarai and my colleague here at Montana State. We went up and looked at this fault that I had noticed in my PhD near Kumjung. And what we see there, so looking at this outcrop photo, there's older fabric here near the sample labeled 3C. These are also make up the staircase going up along the trail here, but this is bedrock right here with an older fabric that's been cut by a younger shear zone. So we went in and sampled in that area. And at the time of my dissertation, I had sampled in the same area or a similar area along strike and found extensional deformation in this zone. So we went back in and actually confirmed that. And it's sort of an interesting, it's a beautiful outcrop, but that sample 3C and 3D was taken from the kind of the adjacent area. But there we see thrust deformation in that older fabric with a fairly north dipping lineation or north plunging lineation on a north dipping fabric. And the deformation, while these arrows point different direction, here's the lineation pointing to the left in this slide and pointing to the right in this slide. But the idea here, it's a thrust sense, so up lineation in both of these. So older thrust deformation that's cut by this younger shear zone, a more oblique lineation, and this gives us a right lateral extensional deformation on this younger shear zone there in Kumjung. Okay, I just want to briefly show some work in Pakistan. And again, I mentioned early on that our syntaxes are also quite complex, a lot going on in this area. And one of the differences that we see in Pakistan is the presence of an island arc terrain, the Kohistan Island Arc. So it's outlined here where my pointer is on this right-hand simplified geologic map. We're going to be zooming in on this area and you'll see this shape again. So we've got the Indian Himalaya here, an island arc, and then the Asian continent would be to the north. And I won't say a lot about this area, but we worked in here. This was David Spencer and myself back in 1989. Worked in this area between Babusar Pass and Nanga Parbat, but primarily along this main mantle thrust or the zone of deformation around that. We found extensional and left lateral deformation in this area, probably related to the exhumation of the high-grade rocks that make up this Nanga Parbat syntaxis. But I will say that that area has some of the most spectacularly exposed geology. It's a more arid climate than Nepal, so less vegetation, very well exposed rocks. It's a much more complicated area to work politically for many reasons, and it changes on a moment's notice, but just a spectacular region. Okay, I want to come back to this area on the Dudh-Kosi River. So again, I had worked here in the 1980s. I came back in 2016, and following that work in 2016 was on Google Earth. I spent a lot of time on Google Earth, and I was looking at this area here in the red box, trying to locate one of the samples that we had collected in 2016, and I noticed this funny topographic feature here. So you can see this linear, I think there's arrows that'll pop on here, linear zone between the two arrows, which to me looked like a fault zone, like a younger fault that was expressed topographically. And so I went back in 2017 with a graduate student, Neil Seifert, and Ananta Gajarel. A few students from Tri Chandra accompanied us as well in this. And we investigated this and found out that sure enough, it is actually a fault zone. It's got a right lateral extensional deformation sense on a slightly southeast dipping plane. This is just a photograph looking up from that same area that was in the Google Earth photo. We call the fault the Benkar fault zone because the little village of Benkar is just down below here. And we named this the Benkar Notch with the zone going right up through this notch. And in the far distance, we're looking at the peak of Tabache. And in a second, we'll look at a close-up of this ridge of Tabache where the fault zone actually continues on up northwards. So here is that photograph of Tabache. This is a leucogranite, exposure of leucogranite here on the far left. And I think you can see the shear zone that cuts right down through the face here. And you can see sense of extensional deformation on it. Of course, I have not gone up and sampled right on this zone to see, but where we do sample part of the zone, and so it's heterogeneous deformation. It's a little bit distributed, but we have other zones more accessible, and that's where we get the right lateral extensional sense of movement. And so this is a map from Seifert's thesis, and the area outlined with these kind of pink lines are the areas of deformation. That peak of Tabache is here, so we were just looking at a shear zone cutting across the ridge of Tabache, but there was deformation distributed and a little more accessible in some of the areas around. Our conclusions on this from this work, it's a northeast striking zone. It's got normal right lateral movement. We did do a traverse across and got some preliminary ages. All we could tell, these were argon ages, is that deformation is younger than 12 million years, but we don't have a tighter timing constraint on it. Since that time, I kind of dove into the literature to look up other cross-strike faults in the Himalaya, and have found out that a number of structures have been recognized. We'll look more closely at those in a second, but also it's quite striking that the strike of that zone and some of the others aligns quite closely with many of the large extensional zones that cut across Tibet. So one possibility for faults cutting into the Himalaya is some sort of continuation of these extensional zones, but this is yet to be determined. It depends on the ages and the timing and a variety of other factors. So here's just a Google Earth image again, but with the outline of some of the work from a variety of authors, and there are others as well that I've not included on here. So here's our little Benkar zone up in the higher Himalaya that we worked on. Several of the structures that have been known in the literature for a while are actually in the in Tibet, geographically sort of Tibet, coming down and just cutting into the higher Himalaya. So the Amadrime, the Yadong feature, the Takala Graben, of course. I'd say the Western Nepal fault zone is a little bit anomalous. I mean, it's not the same as our cross faults. I'm calling these cross faults. It's aligned with the Karakoram fault structure, and I think probably serves a different purpose. The several in India, so Malay Mukul, Vinny Srivastava, and others have worked on the Yamuna and the Ganga structures. And in particular, their work's been at the front of the range where there's sort of boundaries between reentrance and salience of the range. They've also worked to the east in the kind of Sikkim region in India here on the Gish structure, where there's again quite a recess in the range here. That zone does align with the Yadong. These other structures have not been mapped up to the north. We have not yet mapped the Bankar to the south. I've got a student now, Bibek Giri, who will hopefully, if we can travel again, get back in working on that. There are a few structures that are quite interesting outside of the Kathmandu Valley that probably fit this as well. So just a few of the structures that we're aware of. This is kind of the same area, the whole range here, but shown in a geologic map. Thanks to Bibek for making this map or compiling this map for us. But what we've shown here is that these structures, while they do align with extension in the Tibetan Plateau area, they also align with basement structures on the Indian subcontinent or in the Indian basement. So they may relate to that. So we hope to figure that out in the future. But one of the more interesting or other interesting features that has this kind of northeast alignment is the fact that earthquake rupture seems to be segmented in the Himalaya, and this has been known for a while, of course. This is aftershock data from the 2015 earthquakes. And what I want to point out in this slide in particular is the abrupt edge of that aftershock data on the eastern side, aligned subparallel to our Bankar zone. The Gauri Shankar fault is in this area as well, has a similar structure, but again, it's been speculated and not mapped itself. In 3 dimensions, so looking at depth data, there's also an interesting transition to the west of Kathmandu, where the depth behavior changes, and it's been proposed there's a lateral ramp or something else in that area too. So what I would say is that these cross faults may have relevance in limiting the lateral propagation of earthquake rupture. If that's true, then they are very important structures, because by limiting lateral propagation, we limit that rupture area, which is going to eliminate earthquake magnitude and earthquake size. So we need to hope for that to be true and to have many of these cross faults, which will keep our earthquake size smaller. Anyway, yet to be determined, and we hope to launch a study to focus on that specifically coming soon. I'm going to change gears now a little bit and look at some work that Bibek and I and Ananta were involved in, and a number of Nepali students. Hopefully some of you are logged in. I think I saw Lal, but there may be others watching on Facebook. But last year, the National Geographic Society sponsored an expedition to go in, and really the focus was to look at climate change in one of the most extreme parts of our planet, and that is highest elevation area, so in the Everest area. So I'm using the same map that we just looked at, but we went in with 2 teams of geologists and came up together with our 2 teams of 12 people total. 6 split off and went up into this area up towards Dingboche looking at moraines, and our group of 6 came up this valley of Gokyo, and we cored 2 lakes in the Gokyo Valley. We also sampled some ancient lake deposits that Ananta had noticed, Ananta Gajarel, a couple years ago in the Namche, Tengboche, Fortse area, and did some OSL dating. We actually ended up using IRSL, which is infrared rather than optically stimulated luminescence. I'm not going to present that result today, but we'll take a look at the lake coring. So this was an interesting project. It's, again, talk about extreme environments up the Gokyo Valley. When we got up there this past year, so 2019, the lake still had a lot of ice on them. And we ended up coring not the lake we'd originally intended to for a variety of reasons, but here we are on what's called the second Gokyo Lake. So you might recognize Bipek here in this boat in Ananta. We had two rafts that each weighed 8 pounds, so they're very lightweight. They collapse, and actually they should still be residing at the Tri Chandra campus right now. We lashed them together with kind of a plastic tube frame that allowed us a space in between to drop the core device down. And so this is a photograph of that coring device here. It's a plexiglass, well, in fact, here it is on the boats. It's a plexiglass tube attached to this sort of metal apparatus here that's a cylinder, a weighted cylinder that's on its own rope. And we can pull this cylinder up along that rod and drop it down, and it basically hammers this whole device down into the mud at the bottom. So in this photograph, the plexiglass tube is buried down in the mud. And what we ended up with, we sampled 2 lakes, that second lake as well as the first lake. We took 2 cores from each. So one core is here, 1 core from each lake is here in the US, in Montana, and 1 core is from each lake is on the Tri Chandra campus. The first lake was a very shallow lake. That's where that photograph was of the apparatus at the bottom of the lake. Gave us nice layered sediment. The second lake, however, has a nice fold in it here and some other deformation features that Ananta has been looking at more closely. We had some radiocarbon ages taken for these samples, and the oldest part of our core, and our core did not go to the very bottom. If we had better equipment, we would be able to get down deeper, but we got down to almost 2,000 years, so about 1,800 years. So we're looking at 1,800 years of sediment here. Here at Montana State, we've done some pollen work, and the conclusion of the pollen work is that there are more forest species in the younger layers of sediment, whereas it was more grass and shrubs down below. That just means that, so remember, pollen can be blown in from farther away. So it does mean that we've got the forest encroaching during this 2,000-year time period. So as it's in part of the warming following the end of the last ice age. So we've had warming since 10,000 years, we know that. But this is just consistent with that last 2,000 years time period. Ananta's been looking at some of this deformation more closely and has concluded that some of the sediment disturbance may be fault or earthquake related. So he sees even in some of these nicely bedded layers evidence for disturbance. So an interesting story about deformation and faulting in the area that can come from lake coring as well. Here was the geology team. So hopefully some of you that are in this photo are in the audience and are listening, but Ananta and I are holding the core tubes that we got from each lake. Master students from Tri Chandra, Bibek Giri in the middle here. And with that, I want to thank you, and I'll take any questions.
Thank you. Thank you, Mary, for your excellent presentation and wonderfully covered most of your research areas. And very interesting to see that you are expecting or analyzing the seismites in the Gokyo Lake. That would be very interesting finding. And then, of course, this arboreal pollen and non-arboreal pollen, that if you can identify that, then it would be interesting to analyze the paleoclimate of that region during the formation of that area. Yeah, I have particular some of the interest, but I'll come later on with some questions, but let me take some of the questions. So I'll take first question from Facebook. So Praveen Shrestha is asking, can you please elaborate a little bit on channel flow methods? Mary.
On channel flow methods. So this is not actually a topic I've really worked on, but the original channel flow hypothesis was, well, put forward conceptually, but then was modeled numerically. So you can look those papers up. I don't have the references exactly, but a lot of that was numerical. And then some of the other methods that have been proposed have brought into light more some of the geologic features that are in there. So again, I'm not sure what exactly your question is with methods.
Yeah, there are lots of models about channel. There are lots of models explaining about the inverted metamorphism and during the evolution of the Himalayas, and particularly there are a couple of papers that Praveen might be interested to read. You can follow that paper. So I will take one question from Junu Preti in Zoom. So asking, the Gorkha earthquake was around a magnitude of 8, but similar earthquake like Loma Prieta has a much higher amplitude, but Gorkha earthquake was much of subdued amplitude magnitude, highly damped. Is it related with the nature of this cross fault in the Himalayas? So do you have any observation, Mary?
Not observation, only speculation. So yeah, actually, I'm not sure what the Loma Prieta rupture area is, but I suppose you could look that up and do a comparison of magnitude and the rupture area of the two. And you can see the rupture area. I mean, you could use some of that aftershock data to get estimates on the area. I think that work's already been done, but you could make that comparison. So yeah, no, it's just speculation on our part that cross faults may play some role. There is, looking at some of the earthquake data from Eastern Nepal, there's some really interesting features where there's linear traces of microseismicity that follow kind of a northeast strike, suggesting that there's been some microseismicity along a structure that might be a cross fault. So that's our questions are, yeah, do you get earthquakes along cross faults? Do the cross faults limit seismic rupture, or both? Obviously, it could be both. So yeah, there's work to be done both geologically in the field, looking at kinematics along fault zones, identifying fault zones in the field. In a lot of ways, I think our mapping of the Himalaya is still at a pretty elementary level. We've got the broad picture, but for a variety of reasons, it's really tough to do really detailed mapping. I mean, one limitation is access in certain areas, and the other, of course, is exposure.
Yeah, absolutely. It's not that easy to work in the Himalayas, so that's why we called Himalayan expedition. And we could imagine that when Baudret, Fuchs, and Frank did their work in early 60s and 70s, now it's quite easy, but it's still, it's very hard to reach on that areas. So another question from Ajay Rautela, he is asking somehow related, so how you can identify thrust or fault without any map, maybe geomorphologically or something like that. Do you have any explanation on that, Mary?
Yeah, so that's, so Google Earth, I think this is why I spend so much time on Google Earth. Well, partly right now, because I can't get on an airplane and come visit you, but young structures can be very influential on the topography, so that you can often find them by topographic features. And of course, that's true, much more true for steep structures, so steeply dipping structures, because they'll make such a linear trace, as opposed to a low angle structure that is going to be a little less obvious to see. But once you're in the field, of course, we look for evidence. So you don't need a map. You just need to be on the ground looking at the rocks and looking for fault fabric in the rocks. And that's what we need to do more of. but it takes
Okay.
time and it takes money.
Yeah, of course. So I'll take another question from Bimal Singh, which is a very pertinent question. So which direction do you think these cross faults are propagating? For example, northeast to southwest or southwest to northeast? Or how do we determine? Because in the Thakola Graben, during my PhD, I found that these thrust faults were northeast to southwest. So what about there in Everest region?
Yeah, good question. So one of the things we want to do coming up in the future is look at one of these faults from the higher Himalaya all the way down to the foreland. Because I think that's where we're going to get a sense of what's been going on. The fabric that we found in the higher Himalaya is, I call it brittle ductile. So it's stretched out some minerals like sillimanite. The lineation is largely along plains of sillimanite-rich plains and alignment of sillimanite. Yeah, and so that, if brittle ductile implies a higher temperature, but clearly where the cross faults have been looked at in the foreland, they're cutting the main frontal thrust. So they've been active very recently, and they just create fault gouge. They're very brittle structures. Those rocks have not been buried deeply. So does that mean that these structures have been active for a long time? Or yes, is there a propagation? Did they start to the north and they're working to the south? These are unknowns. But I think that our hope is that by getting a seismic network focused on these cross faults, we can see how deeply this rupture is going. So if in the foreland, we've got deformation today that's brittle and it's at the surface, yet we've got microseismicity that's 50 kilometers down, well, then we know these are very deep structures. We know they penetrate the main Himalayan thrust, and they would have a good, strong likelihood of being connected to those Indian basement structures. So I'm not sure that answers the question exactly about which way they propagate, but what we need to do is strive to understand the geologic history of these. How long have they been active? How do they, how are they operating today?
Yeah, it's quite interesting but difficult, question and difficult to answer. Thank you for your overview. Another question from Muhammad Mulhim, asking more overarching question that how different geological structures are from Western and Eastern syntaxes or Himalayas. Some broad overview, little bit.
Okay, so some of those structures are mapped. Okay, they're complicated, and I haven't worked in either area. So, but if you look at the map of, let's just say the Western syntaxis, you see structures that appear almost to be folded in map view. So some of the major major thrust faults that we follow along strike from the central part of the Himalaya up to the syntaxis. Now, something like Nanga Parbat is probably folded in the sense that the Nanga Parbat itself has had really rapid uplift. And so you've basically just taken a fault structure and uplifted a part of it. So that makes the map view appear, that you've sort of folded it. Well, you have folded it in a way through this uplift. But there are places where faults cut through some of those syntaxis structures. So the Eastern syntaxis is quite complicated in its fault pattern. And you'd have to refer to the original literature on people who've been working on that, but there are some really great recent papers on the Eastern syntaxis.
Yeah, thank you. There is one question from Upendra Baral. Is asking, do you think these leucogranites are associated with the UMCT? If yes, then why there is not well exposed leucogranites in whole Himalayan range?
Oh yeah, good question, complicated question. So you probably need a good igneous petrologist for this one, but yeah, I mean, I think that there is a connection between this deformation, between fluids, between the metamorphism and granite emplacement. Why they're not absolutely continuous, again, I think that's going to come down to sort of an igneous petrology question, whether it's availability of fluids or other factors. If you look at it, something like an island arc in a subduction complex, well, you don't have a continuous line of, you do have a continuous string of volcanoes, but you have spotty volcanism. So it comes in certain places and not everywhere. So I would liken it to something like that. And what causes a volcano to happen here and not there, I don't know. What causes a granitic, a melt to migrate up in this section and not that section? Again, I would send you to an igneous petrologist and look at the chemistry and maybe the presence of fluids.
Yeah.
So I'm dodging that one, sorry, but.
Yeah, thank you. So another question from Akshay Outkasi asking, in your model, what you have presented rightly today, so the Greater Himalaya seems to be pop-up of higher grades rock or has a high temperature mineral assemblage between main central thrust and in the Sangpo-Suture zone. Any calibration you used for this assessment? Can samarium neodymium be helpful for the determination of that thing?
Yeah. So for starters, the term pop-up, I guess maybe means slightly different things in different places. I tend to think of a pop-up between two opposing structures in a convergent zone where you've basically lifted something up in the middle. And I think that the higher Himalaya is a little more complicated than that. You've emplaced something of higher grade up against something of lower grade, and you've had a lot of erosion above it. In the case of the Himalaya, in the higher Himalayan rocks, the greater Himalayan sequence, that erosion is both extensional, or that exhumation is both the extensional deformation and the normal fault that's helped exhume those rocks, as well as erosion of rock material by weathering and erosion processes. So that's what's exposed it. And then, yeah, the application of neodymium and how that, certainly neodymium analyses are useful for a variety of things, but in terms of determining the structure of the range, I think that's where we need to be on the ground looking at the faults first and do the dating second, and dating and chemical analysis second.
Yeah, thank you. So I would like to request participant, please post your questions because after 5 minutes, we'll stop taking any questions. So another question again from Junu Preti. I don't know whether you have worked in Arunachal in India, but asking, is there any geological reason why the Kohistan area is like a knot? And same we see in Arunachal area of India. However, the Tibetan region is more bulbous and wide. Do you have any observation on that?
Yeah, good question. Good question. Yeah, so I think you're kind of primarily saying, if you look at the deformation zones, they're very wide at the syntaxes area. Whereas when you look in the central Himalaya, in a way, that deformation zone of the Himalaya proper is much more narrow. And I think part of it has to do with the fact you've got Himalayan deformation coming up, the syntaxis, and then it goes back down. So you've got deformation on the east side and deformation on the west side of your knot. So you've kind of got a double thickness there, as well as, what's at the top of the syntaxis itself. So, so you're concentrating a lot of deformation, but beyond that, I'm not sure I can answer your question.
Yeah, thank you. It needs lots of field work to verify that. I can imagine that. And especially to go in the Western and Eastern syntaxes to understand these things and nearby. Yeah, it takes time, yeah. So again, Akshay is asking, is it possible that the genesis of these extensional cross faults may be due to the overloading of sediments, just like cheese extension model?
Wait, so say that again?
Is it possible that the genesis of these extensional cross faults may be due to the overloading of sediments, just like cheese extension model?
Yes. Yeah, so that sort of, I think, relates really more to the slide that I showed with all the extensional faults across Tibet. So if we've got, and I think this is what you're talking about, the brie cheese extensional model of Tibet flowing out east to west in a sense and collapsing in this. You know, to me, it seems that that extension it has to go somewhere north and south. And so having it sort of reach through the Himalaya is certainly a possibility. So I think that's where in a way it's interesting that both the basement structures on the Indian plate have that same orientation as the extensional structures to the north. And whether that's a coincidence, I don't know. But by looking at if it's purely the extension coming southward, I wouldn't expect that necessarily the seismicity on a cross fault would penetrate the greater Himalayan thrust. I think that you would, I think it would truncate on the main thrust. But if it's related to the basement structures on the Indian side, I think you then have, then there's a good reason for it to go down to these great depths. And there is some evidence that we do have these really deep earthquakes 50 kilometers down on some of them that suggests that there is deformation below the main Himalayan thrust. So yeah, so maybe is my ultimate answer to your question about the cheese and the extension. But I think we still have a lot to learn. I guess that's good job security.
Yeah. Yes, thank you. So again, related with that, Sijan Acharya asking, so by studying cross faults in the Himalayas, can you say that Himalayas is still shifting eastwards?
Is shifting eastwards.
Yeah, maybe he's asking or she's asking about the east-west extensional regime in the southern Tibet and the Himalayas.
Oh, okay. Yeah. Well, again, so that, some of that goes back to those big strike slip faults, which then in Tibet and the boundaries of Tibet, if I'm getting the question right. And those are still active. So, so yes, there is still kind of that eastward movement in that sense.
Okay. So Kishore Adhikari asking about this comparison. Yeah, I think the geology doesn't follow any country boundaries. So only geology talks about the stratigraphy, not the political boundaries. So it doesn't matter one country or another country. I think I will skip that question. So another question from Basanta Bandari is that based on your observation, whether the leucogranite is bounded by STG to the north, or it also has the penetrate to the Tethyan sedimentary sequence along your study area, because he is saying that they found a small leucogranitic vein on the Tethys sequence along the Mustang and Monang area. Do you have any observation in that area? Because I don't know anything about that. This is quite interesting for me also.
Yeah, it is. I guess the question is, has that leucogranite been dated? Do they have any ages or any other chemistry? Can the chemistry be compared? Sounds interesting. And I do know that some of the leucogranites have penetrated shear fabric of the South Tibetan, or are within shear fabric of the South Tibetan detachment, which is partly the basis of some of the early age dating of the South Tibetan detachment. And that's on the Everest side. But again, I haven't worked up in that region, so I can't give you any firsthand information.
Yeah. I also don't know, whether we have, because I didn't find any leucogranites in the Tethyan sequence in the Kaligandaki Valley. So might be, Basanta Bandari, it would be interesting to talk with you later on if you have some, evidences on that. So I'll take one last question from Zoom chat box, and I have a couple of questions for you, Mary. So Surendra Shah, I think you have already presented, but he's asking, mostly in the Dutkosi region, most of the rivers have straight sections more than 10 kilometers. If this is a geographical signature of the cross fault, what's your observation in Nepal or Himalayan region?
Yeah. Great question. I actually do think that a lot of the straight sections of the rivers are fault controlled. And the bad news on that is that if the fault's quite localized and it's under the river, it's really hard to get good outcrop. But most of these structures seem to be somewhat zonal, meaning that there's a bit of a shear zone. So if you can go to those straight sections of the river, find outcrop on either side of the river valley, I think you'll get a sense of whether you've got that cross fault deformation in there.
Okay, so as another question that I will ask to you about, some people said that Higher Himalaya was exhumed before and later covered by Pakistani Himalaya, and some people suggest that it was exhumed later during the Miocene. Or what is the relationship between activation, reactivation of STDS with the exhumation of Greater Himalaya in your observation?
Well, I think that the STDS actually plays a big role in exhumation of the Greater Himalaya in one way or the other. And in some ways, whether it's a channel flow or whether it's a critical taper model, it doesn't really matter. The point is we've got extension there that is efficiently removing material from above the Greater Himalayan sequence. So again, I'm not sure exactly the question here. Activation, reactivation. Yeah.
Yeah, it's quite complex, but it's still, we have to go and we have to understand this activation purely into the field and take more observation. So one particular interest for me is that, the north-south, the western bounding fault of Thakkola, what we call Thakkola fault, some people say that Dagarjung fault, that was activated based on argon iron dating is 14 MA, and which is the part of east-west extensional of southern Tibet, and we have a Caesar-like fault, so that we have tapering down, southern and widening, opening up in the Tibetan side. So that is quite related with the STDS and then to the higher Himalayan crystalline. So particularly in the higher Himalayan crystalline that you mentioned about the Lawford, datings and others. So in your PhD area or PhD time or later in Everest region, because most of the people are talking, there are different stages of deformation from D1 to D5. And that is quite related with this, evolution or the activation of this Himalayan frost and thrust. So what's your observation on that?
Yeah, well, yeah, I'm not quite sure what to say there. So in a way, you walk through the Greater Himalaya and there's not D1 through 5, there's D1 through infinity. But getting, you walk upon a small shear zone and knowing whether it's D12 or D18, you don't know, or we could say even D2 or D4 in some ways. I mean, it's quite complicated deformation, and it's multi-phase deformation. So there's older fabric. Older fabric's been overprinted by younger fabric. You probably have some older fabric, younger fabric with similar strike, so that you're using inherited zones for your younger deformation. There are some beautiful gouge zones in the Greater Himalaya, in the Everest area, so that there's definitely some really young deformation. Where that fits in, I don't know. But again, it's just, it would require, and the topography there just hampers it. The topography and the overburden of, moraine deposits and the glaciers and everything else, where you can't access everywhere to trace out structures. It's so complicated. But I think there's room, for a lot more work to be done to attempt to do some of that, to sort out these different deformations, and to utilize dating methods where we can put fixed times on them so that you can sort out D1 through 5 if you want, and maybe D1 through infinity.
Yeah, thank you. Yeah, that's why, Himalaya is a natural laboratory. We have to narrow down this infinity to a little bit down, and so that you understand the evolution of Himalaya. And yeah, thank you very much, Professor Hubbard, Mary, and then we are very, very excited to see your publication in near future about this lake drilling, especially this core drilling, and whether they have seismites or other biohorizon or biomarkers or pollen, so that we understand this. Because I'm now working on this pollen analysis in the Takola region that I collected during my PhD. So that's quite interesting result. So I'll be very much interested to see whether you'll have a similar or different result in the Everest region. And once again, it was wonderful, wonderful presentation. Do you want to say anything at the last before I hand over to close the session to Suraj?
I just want to say, namaste to everyone, and thank you very much. I wish I could be there and see you all. And thank you to the organizers for putting this together. And what a great way to bring speakers from Nepal to highlight their work, but to showcase it to the world, really, because this is available anywhere on the planet, and then to bring international speakers in that you can showcase to Nepali students, and by archiving presentations, use these in the future as well. So thanks very much, and great job with this series.
Thank you very much. So now I'd like to ask Suraj to proceed and close the session. Suraj, over to you.
Thank you so much, Dr. Basanta, for the excellent moderation as always, and also making this Q&A session very much lively. We'd like to thank Professor Dr. Mary Hubbard for the wonderful review of the works that has been going on. It was really interesting to see the exploration done in regards to the understanding of the complex Himalayas, and we'd be really happy to see the research work, the publications, and also would be really happy to collaborate in the coming days as well. So the Q&A session was also really interesting with a good volume of quality questions. We tried our best to address all of these questions, and the questions were taken from both of our Facebook page live streaming, and also from our Zoom chat box. So if in case you have any further queries, please feel free to mail us at info@inhrr.org. We'll try to solve your questions. I would also like to convey my big thanks to all our organizing team, presenter, session moderator, our guest, and participants for participating in this session. The session was really informative and was really interactive as well. We will be sharing the recorded session on our YouTube channel, and the links will be forwarded to the registered email as well. We'd also like to request our participant to fill up the feedback survey form, and also suggest us some future webinar topics that will be, and we'll try to address those requests as well. So, well, I do have something more to share regarding our upcoming webinar. We'll be having an interesting webinar on disaster risk reduction on this Saturday, coming Saturday on 22nd August. The webinar will be focusing on the use of frontier technologies like UAV surveying, augmented reality, and on DRR. The links will be available soon on Prevention Wave, and also on our website and our social media links. Similarly, we have also scheduled our upcoming webinar on importance of geoscience for achieving the sustainable development goals, key issues, challenges, and opportunities this coming Sunday, which will be presented by Dr. Ganesh Raj Joshi, who is working as a researcher in United Nations Center for Regional Development, UNCRD, Japan. And it will be hosted on August 23. So we'd also like to mention that Institute of Himalayan Risk Reduction will be more than happy to collaborate and organize these kinds of relevant webinar in the days to come. With this, I would like to sign up from our session for today. So I would like to thank you all once again. Hope you had a great time. And I also would like to wish you to stay safe. Thank you. Namaste.
Namaste. Thank you. Bye-bye.
Thanks a lot.